Okay, so first of all, I should remind you that, again, that all experimental physicists wear baseball caps. And I think it's absolutely exciting and delightful that we're talking about two physics experiments that have each pushed the envelope, and the data is coming together soon. No, maybe I'll just do it this way first.
I think you just do it.
Focus. Yeah. Cool. All right. So the goal of the target opportunity program would be to search for the electromagnetic counterpart and all that, and to follow it up with LSST if it's feasible. I'll just go through some of the issues, and to follow it up rapidly, because we want to very rapidly hand off the candidates, if there are a finite number of them, to other facilities for spectroscopic follow-up. And so the first assignment is to assess follow-up feasibility. This all probably has to be done within a minute, and so we have to have we are actually writing an algorithm now in our scheduler for this. There's a hook in it for that. The issues there are the accessible sky at air mass less than 2, if you want to get onto something right away. And that means we could probably spend on the order of 3 hours, maybe less, during tonight, depending upon where it is. You can be lucky or unlucky. It could be setting, which is my luck. And then if it's if it's feasible, you follow it up right away and rapidly get onto it right now within 10 seconds. So we can move anywhere in the sky in 10 seconds. Less than that, 5 seconds. And then we have to decide. Then we have to actually undertake, and this is the majority of my slides, undertake an observing mode which minimizes false positives. So we have a huge background. And then rapidly go over that same area again, 90% probability area, confirming candidates. Are they still there? Or was it something else? And in particular, by doing that, we can eliminate moving objects. I'll describe how that works. Then rapidly announce candidates with their time history. So once you have a candidate, we can go back over the previous years that we've studied this field and give you everything you wanted to know about that galaxy or that piece of the sky and the time history of the transient nature, along with color information, and hand this off to other facilities very early. And so this is just a reminder of what some candidates look like. In the time domain, this is time going from 10 seconds to 10 to the 8 seconds on the bottom, and delta magnitudes going from 0 to 10. And this yellow line here, this is the time scale in which we can react to the detection of anything and issue an alert. And it's also, just by coincidence, the time that we can actually go off and do something else. And so you have all these things. By the way, in the Deep Lens survey, which was my first attempt to do any of this back in the late 90s, we found a class of candidates that still hasn't been classified. It rises at 1 magnitude per hour, and it's extremely blue, featureless blue continuum. Rare, but they're there. And so there are all these things, and we can have a catalog of every piece of the 18,000 square degrees that has information on all of these guys already, once we get to it. And so we also have information for t less than t0. In other words, if you say there's something interesting, we can go back and find the history. As an example, from the PTF survey, there was a, this is a supernova. Here's a supernova, but there was an eruption earlier. There was sorry, this is the supernova. There was an eruption earlier, and then there was a quiet period even earlier. We'll have all this information. So this is the bad news. We don't want any more of these, please. This would be very hard. We could do it. We would have to spend, we would have to spend roughly 5-6 nights. That would use up all of our time for the 1%ers. So we want something better. I just grabbed this, actually at the time of that announcement, I grabbed this off. Somebody here in this room probably made these simulations. Congratulations, thank you very much.
Would you please put my name on there?
Yes. Exactly. So could you just, this is a touch screen, isn't it? You could just, so there's LSST on the Earth, and you could get unlucky. This guy's setting, so you have to wait till tomorrow night. So the holy grail is to have all these guys working. We've talked about that. One worries about late arrivals. And then we've talked about, this is an old slide. I didn't have a chance to download your presentations, but we've talked about various kinds of afterglows. Basically, you would like to get on some of the objects, you'd like to get on them within a minute or 10 minutes. Some of them later. Doesn't preclude that. And others, you might get on them within hours. Would be a good idea. And follow it for a few days. So some of this, and I'll have a slide on it in a second, is going to happen automatically, of course, in the survey. So it's not a TOO as such. We don't have to keep doing this TOO stuff repeatedly every single night. We can do it for the first night, and then rely maybe the second also. It's up to you guys. Maybe wait until the third or something, or logarithmically, and then give up and go back to the main survey. The color changes, and we could track that, which is cool. And then there are these challenges. I think we can do this. Again, it depends on getting on this early, but we can certainly detect these guys, particularly in the redder part of the band. So we go all the way to 1.1 microns. So I think it seems to me, you guys tell me, but it seems to me that this is the place to start. Go red first, see if you find anything, and then go blue, and then get a whole lot of color information. And I'll come up with a strategy, which is just an example strategy. So here's the job: estimate follow-up capability in 2025, and I'm gonna hope that you guys can give us can give the world some kind of classification, if you can get it, of what it might be based on its gravitational wave signature. That would be just gorgeous, because then it would tell us what to do to optimize. But I'm going to assume for this that the reverse is not true. I know less than zero. I think all of us know less than zero about what is out there, and so I'm going to assume that we're not going to choose the way we observe these square degrees with LSST based on any assumption with regard to the stuff I just showed you. We're not going to make an assumption. We just want to cover as many bases as we can. So that means getting out on it early and then tracking it. This, I shouldn't have put this. I mean, the point is to find out, okay? I don't think we should delay and wring our hands over this issue. We just go and do it. There's an issue having to do with the speed of the coverage. Luckily, we have a large field of view. And I'm going to assume in the rest of this, that it's 100 square degrees. Much larger than that, it becomes possible, but it becomes an issue where we absorb all of the 1% time allotted to this kind of activity. Maybe 2%. And it's a political question. Here's the big killer. I mentioned it before. I'll go into it a little bit. Transient object background. We have, foreground maybe. We have a lot of transients per unit time. Maybe not 10 million a night, but a lot. There is this interesting trade that at least somebody talked about during this meeting, the accuracy completeness trade. for classifying objects and retiring them as candidates. And as I just said, I'm assuming no EM template. So there's lots of variables of different classes, and you're not supposed to be able to read this because there's so many. But you know, there are pulses and stars, the cataclysmic variables, the eclipsing systems. But the sky is a very variable place, and every time you look at the sky, you're going to discover new ones that haven't been actually cataloged and analyzed and classified. And so every night there'll be new. And this is the thing that was I showed you before that was supposed to scare you, which is the number of new things that pop off in the night or move per 8 hours of observing during a night as a function of the elapsed survey time. So it decreases because we learn more and more as we observe these guys about who they are, what they are. Each has a personality, and we classify it and retire it from the list of unclassified objects. So this is the new stuff that's variable, that you don't know anything about when you first go to that field on some night, from 0 to 4 years. And so you can see the main enemy, forget this curve, is the main belt asteroids. But these other classes of variable objects are non-trivial, particularly during the first year or two. And I think none of us have a problem with doing all of this activity out here, which makes life a little simpler. But still, you're talking about several thousand per night.
So does this graph captures, there's a difference between new and new. There's a new object and a new signature. Does it capture the difference between those two news?
Not initially. That's the point. You don't know what initially. Right now, if I go to this over here in the sky, and I've been working for 2 years on the main survey, I know a lot about what's in this part of the sky, but I'm going to find new things. At the moment they're observed, we know nothing about these new things. But very rapidly, and I'm going to get there, very rapidly they will be classified within minutes.
Okay, this is what I'm asking.
There'll be an attempt at classifying them. Okay, so I'll get to that. And so what about this main population of vermin? Asteroid size distance relationship. There's the main belt, and then there's the Kuiper belt. Here's Pluto up here. This is the size of the beast in kilometers, up to 10 to the 4. Congress has told us we have to find all of these potentially hazardous ones. But the main belt is further away, and it contains a whole lot of stuff, and that's our enemy that we have to. Those are the guys that we have to characterize and retire or avoid somehow. And this is to a single exposure. This is a single exposure going, a single visit rather, going to about 24 and a half or so our magnitude. So it's these guys out here at a few AU that are the problem. And since they're so close, though, this is the advantage. They're actually moving because we're moving around the sun. And so I'll get to that in a minute. I won't dwell on this. So there's a certain probability that you will actually discover an asteroid, and it goes to 0 if it gets too faint. That's the whole purpose of this thing. So we'll find about 6 million of them, and that forms this background. There is also a little bit of an embarrassment that is, so we're configuring the observing to optimally discover an asteroid repeatedly over several revisits during several weeks, and then we can link those positions, and that's called the linking problem. And if you have too many of them, it becomes a really impossible problem. So we want to we return to the same piece of the sky within an hour or half an hour. We go at this accelerated cadence we were talking about. And link these guys up and then get their orbits. And then then that guy's been retired from the class of things we know nothing about that are moving on the sky. So they don't contribute to that curve that I just gave you. But only after that linking has occurred. But we will also lose those occasionally. And that's the arc length problem. We'll have we'll find these asteroids, and there'll be an arc, because they move. There'll be an arc in the sky where these asteroids are moving, and eventually we'll lose track of it. It just happens. And so there'll be a linked asteroid, and then it'll be lost, and then it'll be found again. And as soon as it's found again, it's a new unclassified object.
You mean like it'll go behind the sun and you won't have sufficient,
There are all sorts
you
of...
won't be able to
Yeah,
extrapolate?
Yeah. There's an inch worth of paper on this issue. It's tough. Anyway, but that's worse the fainter you go. So I just wanted to mention that there's the Lost and Found department. There was a survey which was better than the SDSS called SCADS, which looked at a much smaller area of the sky specifically for asteroids, and that's the blue curve. And so the number of main belt asteroids discovered in millions as a function of years into the this is transferred onto LSST now. This is the LSST survey based on these other surveys. The predicted number of asteroids per year discovered. Cumulative number discovered as a function of year. And you can see you're up to 6 million after about 4 or 5 years. So this is the solution to our problem. They actually, if they're main belt asteroids, they actually move because they're only a couple or a few AU away, and that's in this region here, and they move about 10 to 30 arc seconds per hour. So you cover this whole area, and then you come back in an hour and cover it again, and they move by 10 to 30 arc seconds, and that's a fairly huge motion compared to our 5 milli-arc second position accuracy on detected objects. So this is how you retire most of them and get around that huge background. Here's another way that you do that. Unfortunately, it means less efficiency for LIGO follow-up. This is the ecliptic. This is a remap of what I showed you before. So this is what solar system astronomers think in terms of. Their world looks like this. This is the ecliptic, and colored here from 0 to 500 is the main belt asteroid density as a function of position in the sky. This is ecliptic latitude goes this way. So if you are more than about 10 or 20 degrees off of the ecliptic, you're way down by an order of magnitude in terms of this background. So that's another really nice thing to do, but this simply means that if the LIGO 90% air circle is here, that's a really delightful situation. If it's right here, that's sort of bad news. There'll be more confusion. So, regarding this challenge, after about the first year, the archival sky will actually be quite deep, to about 26th magnitude at 5 sigma, over the full 18,000 square degree, in all these bands, U, G, R, I, and Z, and Y, all 6 bands. So a lot will be known about the sky. So the static sky will be well known, even the dynamic skies I mentioned. There'll be data on everything that moves and flares after the first year. Unfortunately, the main belt asteroid background is only down by 20%, but I just argued how you might want to avoid, how you could avoid it. The new transients in every night, in an 8-hour night, are going to be about 4,500 in this 100 square degrees. These guys you can maybe get rid of. This is the asteroids, by being clever, coming back and covering them again. So that means that there's going to be roughly 1/2 new unclassified transient per square degree, which is beginning to look interesting. However, the alert rate itself is going to be higher because there are going to be some bogus objects. So here are the requirements for this. Just write them down. Survey the gravitational wave 90% alert area rapidly. Hopefully get finished within the first night, a few hours of work. How you do that is the issue. Cover a range of spectral signatures. So you want to sample this 100 square degrees very well in at least G, R, I, Z, and Y. Remember, we can only have 5 filters in the camera at one time, so I'm imagining where we have this event from LIGO happens and the view filter is out, and we have these filters in. We'll cover it. We'll cover all of these multiple times. And that will allow us to distinguish whatever is out there from the so-called normal optical transients. We want to stay within moderate air mass, otherwise life becomes very hard. So there's probably somewhere around roughly 3 hours of usable, maybe 5, usable time during a given night if you just announce it at a random time that there's something interesting that we could get to. And this, hopefully, this is a requirement. We're not guaranteed, but this hopefully will get the false alarm rate down to a few per night, which means that if that's true, we can just pass these objects off to the spectroscopic community, and they'll be unlucky a third of the time or something. This involves some machine learning random forest classifier. So here's the optimal tiling issue. This is a picture of the LSST focal plane, and the moon is not embedded in the focal plane. This is just to show you the size of the moon. And the idea is to tile the sky very quickly with this kind of focal plane. By the way, there are 200,000 galaxies per exposure in each visit discovered. This is only going down to 24th magnitude.
You said 17,000 yesterday.
Per square degree.
Oh.
Per square degree. This is 9.6 square degrees in here. And there are 200,000 galaxies just in the exposure. Of course, we'll know much more about this area, this 10 square degrees, after the first year. And there are, as I mentioned, more like 300 million galaxies in that same area. And so you don't want to tile by dithering like the main survey. You just want to move quickly tiling the sky. So if you were a bee, you would like this. This is sort of how you would tile the sky, perhaps. A bit of overlap, just enough to not have any excluded areas between your pointings. And so there's a little tiny bit of overlap. You only gain about a half magnitude and limit this is stretch right around the edges of each one of these. And so each one of these little cells is about 7 square degrees and overlaps a little bit. And so you tile whatever area in the sky you have in this way. I think it's the quickest way to do that. This is totally useless for the rest of the science cases. So this is timeout, TOO, useless data for the rest of the community, except there are some people that are interested in transient objects and might be interested in something. But this is not any of the surveys. None of the proposals that we have received ask for this kind of work.
So if we can give you, 10 square degrees, and then would you then be able to dither, and would that make those exposures acceptable for the rest of the survey?
Yes, but it's awfully slow. And I'm going to argue 100 square degrees is really hard. 10 square degrees is quite possible.
Okay.
Yeah, that's a good point. Well, I just made it. So here's an input to the strategy. One LSST field visit is, we haven't actually fully decided this, but the baseline is 2 15-second exposures, which actually takes 35 seconds due to inflation. Then there is a slewing that goes on. We have to slew between fields. That takes us 5 to 7 seconds, depending on how far we have to slew. This may be replaced by a single 30-second exposure, which makes this a few seconds less. Anyway, there's on the order of 40 seconds per visit. And so each one of those little cells, you could imagine, would be 40 seconds of work. Then you move to the next one. To do 100 square degrees, that's about 16 fields due to this overlap. 16 LSST pointings. 16 LSST visits to do 100 square degrees. So that'll take about 60 minutes. There's about an hour to survey 100 square degrees in G, R, I, Z, and Y, going from 0.4 to 1.1 micron wavelength. There'll be about 590 new transients that are unknown, that haven't been classified. And of course, we got rid of these other main belt asteroids.
So you're saying basically an hour allows you to survey in five filters.
Yes. Now,
100 square
you
degrees.
wouldn't give up. I'm going to argue that that's just one pass, and I argued that you can't retire the 6,000 without doing a second pass. So we have to do a second pass in order to retire that 6,000. Otherwise, it's impossible. You see the problem here. Factor of 10. So we want to get rid of these guys. So here's a proposed strategy. It's just one of many possibilities. I just dreamt this up one evening. You cover the 16 fields in single visits in this sequence: Y, I, R, Z, G, I, Y. Ask me later why I thought that was interesting. But anyway, you start in the reddest possible band. Maybe I'm wrong in thinking, but I mean I think that everything I've heard at this meeting, these guys are going to be shrouded in dust. Maybe red. I don't know. Anyway, this is an example. Y, I, R, Z, G, I, Y. You do that. You do that sequence. And that's going to take about 1.5 hours to do that, including filter changes and slews. And then you repeat it. You have to repeat it. You repeat it 3 times. What does this get you? It gets you a lot of color information, and it allows you to retire all these other background objects, like supernovae, etc., that have funny colors. You have a 6-point light curve in I and Y, plus some GRZ color information. In the first YIR pass, if you go through and just do YIR, in that first pass, there's still going to be 320 new unclassified objects, but if you do a second pass, this 3,500 goes away. So that starts to look a little bit interesting because you can use other filters. So we need a classifier that has a false positive rate better than 1%. Those already exist, happily. People work very hard on color classifiers and time domain classifiers. But you would also like to have an efficiency greater than, say, 80%. Otherwise, life gets iffy. This is definitely possible for some transients in the background. It's been shown. There are random forest classifiers that actually achieve this. ZTF is going to teach us a lot more about this, so we'll know a lot more in the next few years about this issue. And we're going to happily, Eric has joined our team, Eric Bellum, and we're going to learn a lot together.
Doesn't this depend a lot on what you allow as the possible EM counterpart? I mean, what's the basis of the classification?
This is not a classification. Sorry, I misled you. This is not a classification. The enemy is the background, not the electromagnetic counterpart.
Okay.
We want to classify that background and get rid of it.
Meaning that the set of seven different things.
That's
So
what this is
this
about.
this is, you're saying, for the main belt asteroids and the supernovae and all that, this is what you can achieve.
Right.
So,
Yeah. So we have to get rid of that 590, and this is how to do it. And then rely on a 2-hour revisit to exclude asteroids. And so we need to get the false positives down to a few per night, and then hand off immediately to Gemini or some other spectroscopic follow-up facility. This is just an example from somebody's, I forgot the authors, but this is based on DES data of a maximum likelihood random forest classifier showing the accuracy completeness trait. So you can, you can be over here or over here. And there's a magic. Everybody has their favorite spot that they would like to be. Obviously, they've done a very good job with the random forest. This green line. So you'd like to have some efficiency for misdetection, but you want to have your false positives low. So you want to be over here somewhere, and that's doable. So as I mentioned, our backs are against the wall here with regard to a conflict of timescales. So there's this need to hand off some kind of classification to a spectroscopic facility, but it takes us a while to actually do that. Question back.
Well, I was going to say, some of this assumes a priori that whatever the optical counterpart is will be long, and a lot of people that's their favorite scenario. But if the optical counterpart is actually really, really short and prompt, then in some sense, some of the background problems solve themselves.
Yeah, I'm going to get to that.
Awesome.
Yeah, yeah, yeah. That's why you want to get on it fast and cover that full 100 square
Yeah.
degrees very fast,
Yeah.
in the Y band, and then cover it in the next. Yeah, exactly.
Because even though
You'll
our
see it.
style localization is terrible, our timing
Right.
is great.
Yeah.
We can
So-
tell you exactly when the thing.
Yeah, you want to actually. There's a sweet spot. You want to actually
Yeah,
get
yeah.
all this information, but you have to get it in the right order.
Yeah, you know,
You don't want to wait till tomorrow night to get the initial discovery.
But
So-
for those, 5 or 6% or whatever that are promptly observable by LSST, you want to start with the bluest filters and work your way redder.
So I was told you want to start with the reddest filter, so that's interesting.
Well, if you're looking for kilonova, then if you're following up, like if you start your campaign say 8 hours after the gravitational wave trigger, then yes, that makes sense to start red. But if you follow up,
Okay,
say
so
an hour or
This
2
is what I'm
hours-
looking for.
Yeah.
So
Yeah.
you just told me I should replace my Y's with G's.
No, I'm saying it depends on.
It
If
depends
you
on,
can
it
get on
depends
that
on
first
when,
hour, if they
it
get-
depends on when you get
Or even
on.
a few hours.
Yeah.
If you get on early on, it should be blue.
So I'm hoping that we can respond within seconds, okay? And so,
You should look blue
Then you
first.
should look blue first.
yeah, sure, no problem, easy. Can't do U-band.
But if your first pass is one day after that, or
Then that's a different,
And then
maybe then,
Then it's a
exactly.
different
So it's
story.
an
Then
adjustable
it's-
algorithm.
yeah.
Right, okay, good. All right.
So there are no alternatives to TO. You can't repurpose the usual cadence.
I'll get to that later.
Okay.
Yeah. Anyway, so we want to get the false positives down. This is a good way to do it.
Can you come back to that slide for a second?
Sure.
So this is, you're showing false positive rate versus misdetection rate.
Yeah,
But
this
does,
trade.
that makes me think that this is not, I mean, if
It's
you only
what?
have these two classes, and that makes me think that this is like a real bogus classification.
It is.
and not-
This is what a real bogus class.
Right, but you were previously saying you needed a 1% false alarm rate for discrimination, separating
includes-
photometric
Well,
classes.
this includes discrimination with type. There's a group called Antares that are attempting to do this, and this is the broker issue.
Right, but so you need,
I have to leave, so let's
Okay.
get to brokers at the end, and then I have to go. So we need accurate classification to create a high purity sample of electromagnetic counterpart candidates. And to do this, we need repeated TOO follow-up over a somewhat longer time series, maybe several nights, you guys decide. And again, this is probably going to be driven by hopefully some information in the gravitational wave signal as to what the candidate might be. However, this, as I mentioned, this is in tension with the need for rapid handoff to spectroscopic follow-up. And they're going to hate us if we give them junk, so it's an issue here. So we need to optimize the strategy. However, the main survey comes to our rescue. The long time scales, as we were discussing earlier, are actually covered by the main survey. The main survey is going to cover every patch of the sky in that footprint of LSST multiple times a night, anywhere between 2 and 4 times, multiple times a week, anywhere between 2 and 4 times a week. So that's sort of nice. We don't have to have the TOO mode. We don't have to break our survey strategy in order to follow up this 100 square degrees going forward after the first night or two. So just to use the main survey for that monitoring, we can actually, without much effort and without making anybody mad, we can actually rejigger the LSST schedule such that we cover that area in a particular way, as long as we observe it in the same kind of fashion. And this would cover, we could do this modified scheduling for at least a month, I would think, with little or no impact on the main survey science. This is just an example of a plot of the inter-night revisit rate, and that's something we can fiddle with regard to this cadence of working on 10,000 square degrees per month instead of 5,000 square degrees. This is all adjustable. So here's an interesting problem that I hadn't thought very much about. Suppose we get in LSST survey to a situation like this, these guys individually are what, maybe 10 square degrees, these little guys. So we would probably just do a pointing on each one of those and move on. And the slew time is rather short, so we could cover all of this in the way that I was imagining a hexagonal close packed crystal in my picture I showed you. We could just cover this by zipping between these, maybe a couple of pointings for some of them that are a little long. No problem. So there's some open issues. We want to specify what filters are actually used in the TOO mode and in what way, in what order. We have to specify the inter and the within one night and between night sequence. Maybe it's going to be different, as you mentioned. Maybe we tonight we start with the G band, and tomorrow night we start with the Y band or something like that. We have to optimize the coverage of these multiple event areas. I think that's going to be easy. And then there's this post-survey monitoring. The regular dithering mode is much, much slower, but it'll do the job, and we'll cover that area. And again, we can dial in for a while a modified filter sequence if you think that would be a good idea in the weeks that follow. This is just a plot showing the area that we're going to cover. We do, however, probably for this project we're discussing, we want to avoid the galaxy. This is too much happening there. It's just a mess. Forget the galaxy. So that constrains the area that we can cover a little bit. And so in summary, unclassified new transient backgrounds are the challenge, but we could cover 100 square degree, 90% probability LIGO area. It's possible. We could do that in the TOO mode. Overall optical efficiency, however, is only about 5%. I think somebody mentioned 6%. It's interesting that we calculated almost the same number. Due to the fact that the LSST can cover only a fraction of the sky, the 5 to 24-hour ratio, we can work 5 hours tonight on some area maybe. The fact that we want to avoid the galaxy, and then there's weather. And so the joint efficiency is a few percent. I don't think we should worry about that. We should just go and do it. But we need to optimize the TOO strategy in a mix of TOO with the main survey weekly coverage. And there's probably some traveling salesman problem that we could try to solve that would optimize stuff, and that's it.
So only ask a question if you're willing to risk that Tony will miss the flight because of you.
But he does.
This is more fun than
The one piece of information that, I mean, it wasn't seen to me how this came into was the fact that we know the LIGO sources are close. And so, you know,
Yes.
even if they get kicks, they should have an association with nearby galaxies.
Yeah, so those galaxies will be a complete catalog of those galaxies out to a gigaparsec, actually, after the second year. And a lot will be known about them, including the time history of any variability, maybe it has a AGN, etc. The shape of the thing, there'll be color images
So
that we
if
can
we
give
restrict
you.
to like,
Part of the classification, in other words.
well, I just
Yes.
mean, yeah, if you just took these false positives and you only looked at the ones that were within
Oh,
3
yeah.
or 4 stellar
Yeah.
radii,
But
a
that's
galaxy
making
within-
an assumption that I was not
Okay.
allowing myself
Yeah.
to make, because I know less than zero about these sources. Maybe you think that it should be places of high baryon density. If that's true, then yeah, somebody could do that.
Does this take into account the moon?
No, that's an annoyance. So we only point. So in the Y band, we can point within
This is
5
blue,
degrees of
that's why
the
I'm
moon.
more worried.
Say again?
The prompt one is blue, and that's why I'm more worried.
Yeah, that's a very good point. So the moon, I don't even observe when the moon is up in the blue band. It just pollutes the night sky pretty thoroughly. In the Y band, I can observe within 5 degrees of the moon. Yeah, that's a good point. So there are other issues. Anyway.
Okay. Thank you so much, Tony.
Okay. All right.
Very nice. So we're gonna break for a quick lunch. The food is there, so you don't need to go anywhere. And let's be back in like 45 minutes.